Hello everybody, my name is Auden Choi and welcome to Lab Report 5 on Magnetic Braking with Faraday for Physics 2212. Here's a table of contents. So the goal/purpose is to collect observational data of a magnet falling through a conductive copper tube, model the magnet/tube interaction computationally, and compare computational predictions with your observed data. Note the goal changes slightly due to a mistake in the last lab, and now we're just comparing our measured value to a computational magnetic dipole moment, which we're just finding a magnetic dipole moment whose time is similar to the experimental time. Assumptions is that magnet acts as a magnetic dipole, there is air resistance is negligible, and gravity magnetic field of the copper tube were the only forces acting on the magnet. The fundamental principles is Newton's second law, Ohm's law, Faraday's law, and Biot-Savart law. Previews at the experimental time I got was 12.78 seconds, and the computational model time at roughly around 12.8 seconds, we have a magnetic dipole moment of 1.29 amps meters squared. With the materials provided, we are finding the measurements of a tube used to measure the time it takes for the magnet to fall from one end of the pipe to the other. Here are the initial conditions. The length is 1.005 meters, width/thickness is 0.001 meters, inside radius is 0.0065 meters, total radius is 0.0075 meters. The magnetic dipole moment from lab 4, I got 17.2 amps meters squared, but this will be changed into a finding a theoretical magnetic dipole moment instead, in which its time is similar to our experimental time. The mass of the magnet is 0.023 kilograms, and the time it took for magnet to fall through copper tube was 12.78 seconds. The checkpoint, why can we use a ferrous tube, for example, steel pipe? Steel is magnetic and has a more notable magnetic field. This notable presence will cause a skew in the data. What happens to the magnet? How does this compare to a magnet falling in free space without a tube? Magnet falls through the tube more slowly than it would fall in free space. This is due to the magnetic forces formed from the induced current by the copper tube, which acts upward as the magnet falls. Here for the computational, here's our equation for the Biot-Savart law, Faraday's law, Newton's second law, and Ohm's law. For computational actual coding, here for step 1, we have our initial conditions. And here in the second part of step 1, we have our mass, our magnetic dipole moment, in which we're just plugging in magnetic dipole moments, and we're trying to find a time that is similar to our experimental time. Here are the initial conditions, that vector 0, 0, 0, t equal to 0. Here, step 2, this is to define the dipole, or define B, and this is the formula that this code is based off of. Step 3, we're just calculating the magnetic flux here, and this is the link to the code. Here, we're just doing a simulation loop so that we can model the copper tube and the magnet falling through it. And the rest of these are just representing the field, the magnetic forces, net force, and all of this is plotted down in the graph. And here are our results/observational data. We see this type on this magnet. The top is blue, the bottom is red. We have a magnetic dipole moment of 1.29, in which its timed is 12.8 seconds. Note previously that the length here is recorded as 0.105 meters. This is just for efficiency's sake. So when it's timed at 1.28 seconds, we're multiplying it by 10 to get the actual length of the copper tube. Here we see a divot, a constant velocity, and a drop. So the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? How can you know? Red color is counterclockwise, blue is counterclockwise. This can be deduced using Lenz's law. The law tells us the direction of the induced current due to the change in the magnetic flux, since we see that the magnet is dropped with its north pole facing downward. And what happens to the dynamics of the system when you flip the magnet around? The directions of the current would flip, but overall the magnet would be the same and it would still fall more slowly than in an open space. So how does the total time in the tube of your real-world system compare to that of your computational system? How might the computational system be more accurate? And when finding computational magnetic dipole moment, the times are similar. The time for the computational magnetic dipole moment and time for the experimental are very similar to each other. Here we got like 12.8 seconds, and from our experiment, it was roughly around 12.7. And if I want to make this more accurate, I can try to make it to where when I create the program, I can make it to where the code accounts for like more rings in the tube when like calculating the the force and flux and stuff. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? A large dip in the beginning, force of gravity is greater than the magnetic force. The after some time, we reach a terminal / constant velocity, which shows the force is balancing out, and then another dip is made, which indicates the gravitational force is greater than magnetic force. And here, the experimental and computational values are similar to one another, with experimental being 12.78 seconds, computational model is 12.8, with the magnetic dipole moment that I found was 1.29. Errors when calculating the magnetic dipole moment before changing what our actual goals are now. There were inaccuracies while using a magnetometer from the app on the phone, and also some mistakes I made in calculating magnetic dipole moment, which made some effects for the future computational models. That's why I changed the goals. That's why the goals changed. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the following magnetic change? Ring currents become extremely large, magnetic braking forces becomes very strong, and the magnet slows drastically and may hover into the falling. What if the holes or slots were cut into the tube? How would this affect the ring currents in your model? The ring currents are reduced or blocked, magnetic braking forces decreases, and the magnet falls faster closer to free fall. Conclusion: experimental, computational, similar to each other. When finding a magnetic dipole moment whose time is similar to our experimental, magnet will reach terminal / constant velocity based on the graph made after some time, which represents the forces canceling out. And human errors such as miscalculations in the magnetic dipole moment can lead to a vast difference in time. This leads to a change in like the procedures and goals that we have. And that is it. Thank you for watching.